everybody. I first want to start with a shout out to Mark Reale. He has asked me to, publicly admire him in this video. So, Mark, this is for you. Today we're going to do some challenging equilibrium problems, ones where we have to set up something called an ICE table and go through and solve for the values at equilibrium. Now, in class, we did some problems where we had to plug in values for the equilibrium constant and just go through, plug them in, and solve for them. These are more challenging. You actually have to either figure out what the equilibrium concentrations are or find the K value by doing some work. And an ICE table, it's really just an organizational tool for you to use. ICE stands for Initial, Change, and Equilibrium. As I just highlighted on the screen, it's just a grid table that allows you to easily deal with these concentrations and not have to do them in your head. Now, something that we've done in the past, in the last couple of days here, is we've written equilibrium expressions, and here it is. The KEQ equals the products over the reactants. Notice I'm following where I put all the gases in. I use the coefficients as exponents. But now, when I look at this problem, it says that in a reaction, it started, and that's really key, that the reaction is started with 0.2 moles in a 2-liter flask. Starting means it's at the initial state. And then they say the reaction reaches equilibrium when the concentration of A is 0.078 molar. And they want me to calculate or evaluate KEQ. So what I like to do is I like to set up my ICE table in terms of X. And let me show you what I mean by that. Again, they say that I started with just some A. And so I put that in the initial. I need it in molarity. Everything's in molarity, so I change it to molarity. There's my molarity of A. Notice I leave 0 for B and 0 for C because they haven't been made yet. This is the initial state, the beginning state of the reaction. I then do the change, and this is where people get confused. In my change, you'll see I have X's here. Notice for A, there's a 2 in front of the A, and so because there's a 2 in front of the A, there's going to be 2x. Now notice it's minus 2x, and that's because we're using A to make B and C, just like we did in the CHIP lab, where we took the reactants and made them into products. We used up some of those reactants and formed products. And so we do minus 2x because A is being used up, that's the negative sign. The 2 is for the coefficient, and then x is because we're not really sure how much is changing yet. For B, it's a 1 in front, so it's plus 1x, and for C, it's a 1 in front, so it's plus x as well. You could do plus 1x if you really want to, but I just write plus x. Now the equilibrium row here, this is initial plus the change. And so initial plus the change, for A, it would be the 0.1 plus negative 2x. And for B, it would be 0 plus x. And for C, it would be 0 plus x. And so I actually could put those into my equilibrium expression right here. Now the thing is, though, with this problem, I know A's concentration. Remember, here's A's concentration at equilibrium. It's given to me. And so I could set that equal to the 0.1 minus 2x for A and actually solve for what x is. X is 0.011. That allows me to plug everything into the equation. And then I can solve for KEQ. I get 0.02. The ICE table is meant just as a way for you to organize what's going on. Let's try another one here. Let's try finding a KEQ again. So I'll start this off for you, and then you could solve it on your own. This time they're doing pressure, and that's fine too. You could do pressure or concentration depending on what they give you. So they say 1 atmosphere of each reactant. They tell us, or they kind of imply, that there's no products. The change now is going to be in terms of x. So the reactants get used up. Minus 2x because of the 2. Minus 1x because of the 1. Plus 2x because of the 2. Then I put in my equilibrium. 1 minus 2x, 1 minus x, and 2x. Now again, they gave us some hints here. They told us that at equilibrium, the pressure of O2 is 0.506 molar. Now I know that I can use that. For O2, 1 minus X, I know that it's 0.506. That means that I could solve for X. X is going to be 0.494. And I could plug that into each of these and then solve for K. And it's going to be a huge K. So when you get like 13,000, don't be surprised, but plug that in. KEQ equals the products 2x squared over the reactants 1 minus 2x squared times 1 minus x. Except I know all these values already. I can find them. I can put x in for all of them and solve for KEQ. All right, so these are two problems. I want you to go find KEQ for me. Tell me what you get tomorrow. We can go over it. We're going to practice more of these in class. What if we have the reverse, though? So what if we have a problem where we're trying to find the concentrations at equilibrium and we are, given the K value? Now we won't be able to find X through, the way we were doing it. We'd have to actually go through and search for, what X is. So we have a decomposition of HI forming H2 plus I2. So my reactants are over here, my products are here. They tell us that we inject 2.5 moles of HI in a 10.32 liter flask. So let's change that to molarity. 2.5 divided by 10.32, and we get 0.24 molar. Now remember, this is initial, so in the beginning we should have 0 of the products. Now we do our ice table. I have to balance my reaction. I almost forgot to do that. We would have gotten in trouble here. I need a 2 to balance it out. So this is going to be minus 2x plus x plus x, x, 0.24 minus 2x. Well, now I'm ready to solve for x. I look through the problem, but I don't see anything in there like I saw in the last problem. I need to use the KEQ to solve for it. So when I look at this, my KEQ, it's equal to my products, H2 times I2 over HI squared. So now if I plug this in, my KEQ is 1.23 times 10 to the negative third. That's equal to x times x over 0.24 minus 2x squared. I could even simplify the numerator here, so I could have 1.23 times 10 to the negative third equals x squared over 0.24 minus 2x squared. And this should be like, oh, I can simplify this. That's why I call it an easier problem, because everything's squared here. So I can take the square root of everything, and I can solve for x. So if I do that, if I do 0.00123, that's something like third. If I take the square root of that, I get 0.035. So I get 0.035 equals x over 0.24 minus 2x. And now it becomes much easier to solve for. Now this is what you're going to see as a test level. I'm not going to test you on using the quadratics like we are down here below, but I'll show you how to do a problem with that really quickly now. Basically, you'd have the same setup, except when you try to do the perfect square, you wouldn't be able to. The perfect square wouldn't work out, and you'd be forced to solve for the quadratic. So what I'd like you to do actually, without solving for the quadratic, again, without solving for it, I'd like you to go through and set this up. I give you the equation here. I want you to build an ice table with it. I want you to put in the expressions and, solve for, everything up to where you get basically to here. I want you to do up to this point, right up here for the equation down here. And then I want you to stop and not solve for the quadratic. And I want you to do that for tomorrow. So you have a few tasks here. You have to find for x over here. You also have to find for x over here. and then you have to do this setup without solving for the quadratic. And tomorrow in class we'll go through how to do that together, and I'll show you the shortcut the next night, and we'll do some other manipulations in the next video. Alright, thanks so much for watching.